Hi and welcome to Maths class. Today we're looking at the normal approximation to the binomial distribution. So hold on a second, we've been looking at the normal curve in recent videos. So why are we now talking again about a discrete distribution, the binomial distribution? So what I'm going to show you is that in fact when we have a lot of tests, a discrete distribution, the binomial distribution, can start to look like a normal curve. So let's just explore that a little bit. And what you can see in front of you there is a graph of a binomial distribution where n is 5 and p is 0.5, and you can see those values are written in the table there. So when n is 5 and p is 0.5, this could be, for example, how many heads do I get when I toss a coin 5 times? So my options are no heads, 1 head, 2 heads, 3 heads, 4 heads, and 5 heads. We've seen this before, but it's been a while since we looked at it. So in this example, you can see that the most common things to happen would be 2 or 3 heads. So now let's try something different. Let's look at, now I'm no longer going to be talking about tossing a coin, but what if I still had n is 5, but p is 0.8 instead? Now what you can see there is that the graph is now skewed. So I can see the peak is at x is 4, rather than before when there was 2 peaks at x is 2 and x is 3. And if I change p in the opposite direction, let's make p 0.1 now, I can see that the skew is on the other side, in the other direction. So this doesn't look much like a normal curve. But if I go back to having p being 0.5 and I make n be, let's say 10, so this is now looking again like tossing a coin, and it looks like I've done it 10 times. It's now a very symmetrical curve. So that's the first thing to notice, is that I've got symmetry when p is 0.5. It looks a little bit like a normal curve if you kind of blur your eyes. In fact, this is what the normal curve would look like if I put a normal curve to try and match this. It's actually pretty close, but of course there's a whole lot of differences. It's not entirely accurate. Now what happens when I go to n is 100? Okay, it's gotten a lot skinnier, but it's now really starting to look a lot like a normal curve. And if I draw the normal curve over the top of it, you can see how close it is. So the bigger n gets, the more this looks like a normal curve. And if I go, let's say, to 500 now, when n is 500, that's what it's going to look like. So now I'm talking about 500 tosses of the coin, probability of 0.5 of getting heads. In fact, the most likely things to happen look like being between about 220 heads and maybe 280 heads. Less than that or more than that starts to look really, really unlikely. So my graph is getting a lot skinnier, but it's definitely looking like a normal shaped bell curve. Okay, I'm going to go back to having n is 5 again, and I'm going to skew my graph again, and let's have a look what happens there. Let's make my graph p is 0.7. Yeah, it's definitely skewed. I can see that my peak is at 4 still, rather than I would expect it to be somewhere in the middle, which would be at 2 or 3 or 2.5. So let's see what happens when I increase n. Now I'm going to increase n to 10. It's still definitely skewed. If I increase n to 50, now it's not so much looking like a skewed graph, it's just looking like a bell curve that has been translated to the right. So you can see that my peak is now at 35, but when I look at the columns on either side, it's looking pretty symmetrical, and I would say that's starting to look like a bell curve. And I want you to notice that that peak at 35 is actually the number of trials, which is 50, multiplied by p, the probability of success. So 50 times 0.7 gives me 35. Let's make that really big now. N is 500. This is definitely a bell curve that's been translated to the right. I can see that again my peak is at 350, which is at n times p. What about if my p was, let's say, at 0.2? What's that going to look like? Okay, that has been translated to the left. So now my peak is happening at 500 times 0.2, which is at 100. Okay. I want to show you also that if I start making p really small, like 0.01, okay, already, even though my n is at 500, it's not quite looking like a bell-shaped curve at the moment. And that's partly because my numbers here only go from 0 to 500. So I'm a little bit chopped off. Maybe I'll make that 0.02, see if that makes a difference. Yeah, look, it's still a bell-shaped curve, but the symmetry, I've lost a little bit of the symmetry. So if I really push p out to being very small, then I do start to lose that really bell-shaped curve. So it's really important that I have values within a certain range in order to get this normal approximation. Okay, so what have we found? Let's have a look at this. So I've got some conclusions that I'm going to draw from that. Firstly, the distribution will be skewed when n is small and p is close to 0 or 1. So when p was 0.1 or 0.2, or when p was 0.8 or 0.9, or even 0.7, when my n was quite small, it was really quite skewed. But when I put p in the middle, then the distribution was definitely symmetrical. So when p was 0.5, my distribution was symmetrical. And then when I made n large enough, the distribution was approximating a normal curve. It's still not exactly a normal curve because it's still made up of actual columns with actual width. But as the columns got narrower and narrower, because there were more and more of them, I couldn't see them so clearly with my eyes, and it starts to look much more like an approximation to the normal. It's an approximation. It's not exactly normal, but it's close enough that if you needed to use some normal calculations, you could do that. So in general, when n is sufficiently large, and I'll talk again in a minute about what I mean by sufficiently large, your binomial random variable x can be approximated as a normal distribution, and we end up with the mean. Remember I talked about the peak of those graphs being n times p, so that becomes our new mean, and the standard deviation is the square root of npq, which you can also write as the square root of n times p times 1 minus p. Now my rule of thumb here is that to be sufficiently large, n times p needs to be bigger than 5, and n times p times q needs to be bigger than 5. So for example, if n was 5 and p was 0.9, np is greater than 5. Let's look at that. When n is 5 and p is 0.9. N was 5 and p is 0.9. It's definitely looking skewed, but sorry, not n is 5, n was 10 I said, didn't I? When n is 10, it's still very skewed. But 10 times 0.9 gives me 9, which is greater than 5. But if I now multiply that by 0.1, which is q, that is definitely not big enough to give me a normal approximation, okay? Whereas if I increase my n here by 100, that's going to make both of those values bigger than 5, and it starts to look like an approximately normal curve. And there's where the normal curve sits. Now you can see it's still not as close as some of the more symmetrical ones sitting in the middle, but it's definitely a good approximation. Okay, so back to our notes. There's my rule of thumb then. NP needs to be greater than 5 and NPQ needs to be greater than 5. All we have left to do is one worked example. So I'm going to use this one. And what I've got here is I'm going to use the binomial approximation to the normal, and I'm going to use coin tosses, which tells me, what do I know? If I'm using a coin toss, then I know that P is 0.5. Ooh. Hang on just a moment. Okay, so I've got P there is 0.5 because it's a coin, and N is 100, it says so in the question. I've got 100 tosses of the coin, and I'm looking for the probability that the coin lands on heads less than 46 times. But I'm not going to use my binomial distribution. I'm going to use the approximation to the normal. So now what I'm going to write down is I'm going to write down my mean and standard deviation according to the two formulas that we just saw. Okay, I've just shifted that so you can see it. So we've got the mean is N times P, so that's 0.5 times 100, which gives us 50. We've got a standard deviation of the square root of NPQ, so that's 0.5 times 100 times 0.5, which gives us root 25, which is 5. So what that means I can say is if I've got my random variable x, where x is the number of heads that I get out of 100 tosses of a coin, then x is approximately normal. And so what I'm going to do is jot down that information and then use my normal probabilities to calculate the answer to the question. So I've just jotted that down, and we can see that I've written let x, well, you can almost see, let me move that, let x be the number of heads. Then x is approximately normal with a mean of 50 and a variance of 5 squared because my standard deviation is 5. So what I'm looking for then is the probability that x is less than 46, and I'm going to use my CAS calculator to do that. So I'll just bring up my CAS. There it is. I hope that's big enough for you to see. And so I'm going to interactive, distribution, and I'm going to continuous because I'm using the normal distribution to calculate this. And even though there's no way I can have negative infinity heads, I'm still going to negative infinity because that's the boundary for a normal curve, my lower boundary, and my upper boundary is going to be 46. My standard deviation is 5 and my mean is 50. So I enter that in and I get an answer of 0.2119. Okay, so then I would just write that down to 4 decimal places. Now before I go, I just want to show you one more thing. What does it look like if I actually use the binomial distribution to calculate this? So let's go to discrete, let's go to binomial CDF. My lower bound is 0, my upper bound is still 46. The number of trials is 100. And the probability of success is 0.5. So now I'm not using the normal information. I'm going, this is how I would do it if I wasn't doing the approximation. Now those answers are pretty similar. 0.2421, it's a little bit big, but if I show you this, if I change my upper boundary from 46 to 45, I'm now 0.1841. So the normal answer gave me something in between 45 and 46, and that's got a little bit to do with the fact that less than 46 for binomial actually means 0 to 45, but less than 46 for normal means everything right up to and including a smidge less than 46. So it's not going to give us the exactly correct answer. But you can see that it's quite close. And as n gets bigger, then the difference between those two would be smaller and smaller, and the error would be quite small. So that's the normal approximation to the binomial distribution.